Hello people, I'm Bharat Acharya. Welcome to a new video. So in today's video we're going to learn interfacing of 8259 with 8085. This comes as a 10-mark question, also called designing. You may get designing with any chip, whether it's 8259 or 8255 or 8254 and so on. But once you understand designing of one chip, you've practically understood it for all the chips. The difference between all the chips will be very minor. It's just one line that will change here and there. You will notice that. After this, the next video I'll be making is interfacing of 8255. You'll realize it was all the same. It's just one signal that changed. So anyway, so that's what we are learning. As I said, it comes as a 10-mark question. Out of 10 marks, the first 5 marks are to understand the interfacing between μp and 8259. For God's sake, don't think this is tough. This is very easy. Okay, it just looks crazy. It's very easy. So anyway, that's the first part. And the good thing about this interface is it's the same for any chip. All you have to do is replace 8259, put 8255, 1 or 2 signals will change. That's all. Now, that's your first 5 marks, or the first half of your answer. Then comes this signal, CS bar. This is what designing is all about. Producing chip select. CS bar stands for chip select. Bar means it's an active low signal. That means it needs a 0. So when the signal is 0, this chip will be selected. So students say, sir, if it needs a 0, why bother? Just ground it. Ground gives you a 0. So ground it, the chip will be selected. No, we can't do that. If that was the case, this signal would have never been there. See, when you ground it, you're giving a permanent 0. That means you're saying this chip will always be selected. Now that should not happen. This chip should be selected only when it's meant to be selected. So here is the basic concept of designing. What I'm telling you right now will make you understand the whole idea of what designing is all about. Okay, look here. This is the μp. These are several chips, 8259, 8255, 8254 and so on. If you want to make it simple, you want to understand it simply, think of them as keyboard, printer, mouse, monitor, various devices connected to the μp on the data bus. Now you understand every chip will have its own address. What address? Memory address or IO address? IO address. These are all IO devices. So every chip will have an IO address. Let's say address of 8259 is 80, address of 8255 is 60, address of 8254 is 40. I'm just taking random numbers. You understand IO addresses means 8-bit addresses. So I've taken 8-bit addresses. You get that, right? Now, tell me, when μp sends data to 8259, should it go to all the chips or should it go to 8259? 8259, it's like this is the monitor, this is the printer. Whatever you watch on the monitor, should it also get printed? No way. You understand my point, right? So when it's supposed to go to the monitor, it should only go to the monitor. When it's supposed to go to the printer, it should only go to the printer and so on. But if you understand, all of them are connected to the data bus. That means data will reach right up to the tip of every chip, but will not enter every chip. It will enter the chip that has been selected. That is the need for CS bar signal. The chip that is selected will accept the data, others will not. Are you clear? So first I should send the data or first I should select the chip? Select the chip. Now chip selection will be done on the basis of what? Weekdays, Monday, Tuesday, weekends? No, it will be done on the basis of address. That is why, go back to timing diagrams. When you do designing, you sum up the whole subject. So everything just comes together in one single video. If you remember timing diagrams, in timing diagrams you've seen there is T1, T2, T3, 3 T states for a basic machine cycle. First T state we give the address, second T state we give the control signal, third T state the actual data is transferred. So that's the idea. First T state processor will give the address. Now the address will come out on the address bus. Now since they are 8-bit addresses, it will be on an 8-bit address bus, that is A0 to A7. So let's say the address is 80. That address will be given to the address decoder. What will the decoder do? It will decode. What does that mean? Analyze the address. When processor gives the address 80, the binary pattern is 10000000. When it gives the address 60, will it be the same pattern? No, it will be 01100000. For 40, it will be 01000000 and so on. So for every different address, there will be a different pattern. The job of the decoder is to analyze this pattern and based on the pattern, select the appropriate chip. This chip's address is 80, but for the rest of its life, it will never know that its address is 80. Who knows? The person who has done this designing, the person who's made the motherboard, has done a circuit that will select this chip when address 80 is issued. So whenever processor issues the address 80, the chip gets selected, then processor gives out read and write signals, and based on that, data is transferred. That is the idea. Are you clear? So the processor gives 80, 8259 will be selected, the processor gives 60, 8255 and so on. Doing this whole designing is a 20 mark question. That's the full memory and IO design, the whole motherboard design. This is a 10 mark question where you're not designing all the chips, you're designing one chip. So for that you need the MUPI, the 8259 and a decoder. So you'll be making a decoder. For that you have to make an IO map, and there's a lot of logic to it. Obviously it's not so small, otherwise I would finish the video by right now. I've just given you the introduction, what's happening in this video. Okay, so here we go. The first thing that we see is the interfacing between MUPI and 8259. Now, what do you know? 8259 is called programmable interrupt controller. It is used to increase the number of interrupts. So there are 8 interrupts on 8259, they come into 8259, so that's their direction. When 8259 gets an interrupt, it interrupts the MUPI on which pin? INTR. In response, MUPI gives back INTA bar. So you need an INTR and INTA bar. Are their directions correct? Please observe the directions as well, not only understand the signal. So that's your basic interface. 8259 getting the interrupts, it interrupts the MUPI, gets back INTA bar. Are you clear? Now, something which is common in every chip you connect. Replace this with any chip, this part will be common. What? Every chip requires the system bus. System bus means address bus, data bus, control bus. This is your data bus, this is the address bus. In address bus, 8259 needs only one line, A0. The video that we've made before this, where we learnt ICWs and OCWs, at the end of it when we did the programming, I made you understand what is the use of A0. If you can say that to me now, I'll be very happy. This is the 5th video we made today. It's non-stop 12 hours of video making. Make it worth it. Come on, please answer. This is the data bus. Through this data bus, what will the MUPI send? Don't say data. Okay, we're not joking here. Of course it is data. What is that data? The data is commands. MUPI sends commands. Now how many commands are there altogether? 7. ICW 1234, OCW 123. Now, all the 7 commands enter through the same data bus. How does 8259 identify which command is which one? With the help of A0. A0 can be 0 or 1. If A0 is 0, the command is ICW1 or OCW2 or OCW3 identified by the central bits of the command, 4th and the 5th bit. I have taught you that. Remember? And if A0 is 1, the command is ICW2 or ICW3 or ICW4 or OCW1 depending upon the sequence in which they've occurred. First it's ICW2, then ICW3. I've taught you that also. So you know what is the role of A0. The job of A0 is to identify the command. So whenever 8259 gets a command, it side by side looks at A0 to understand which command it is, and that's how it interprets the command. So for that you need an A0, you need the data bus D0 to D7. Also, data bus is bidirectional. From this data bus, what else goes on that side? The opcode of call, the lower byte of address and the higher byte of address. You know that, right? I'm sure you've seen the theory of 8259 before you watch the interfacing. That's the order in which you're supposed to learn. Now, so there is address bus, data bus and control bus. For control bus, we need read-write signals. In the architecture, there were read-write signals. Read-write signals decide the direction in which this data bus will operate. If processor says, I want to read, data will go to the processor. If processor says, I want to write, data will come from the processor. So read-write always given by the processor. They decide in what direction the data will flow. Read-write are given by the processor. Are you clear? Now, so what we need is A0, D7 to D0 and read-write. Now, what do we connect to them? This is address, this is data. If you know your 8085 basics, 8085 doesn't have a separate address bus and a separate data bus. Address and data buses are multiplexed. Do you remember that? So you have a bus called AD0 to AD7. Now I'm going to take you back to timing diagrams lecture. Now this bus in any operation carries address also and data also. How do you know whether it's carrying address or data? There is a signal called ALE. ALE stands for address latch enable. Say it again. Address latch enable. Now you'll understand the actual meaning of that full form. Come on, this is so much fun. Look here. There is a device called a latch. 74373 is the product number. You can use 8282 also, 8283 also. There are numerous latches in the world. Whichever one you get a grab, whichever one you get a hold of. Anyway, so we are using 74373, the standard textbook latches used by Gaonkar, one of the most prescribed books of 8085. Anyway, what does the latch do? Suppose this is a bus. Okay, I send 25 over here. 25 will come out from here. No surprises. Whatever you send, you'll get that. But after 2 minutes, if I look at the bus, will it still carry 25? No. Because a bus is used to transfer value. What is the value? Current. What is the bus? Wire. Current passes on a wire. Current doesn't reside in a wire. It doesn't get stored in the wire. But if I want that after some time also, if I look at this bus, it should still carry 25. Then I need somebody to hold the value. That is why we put a latch. What does a latch do? It captures the value. A latch is a set of flip-flops. A flip-flop can hold 1 bit. 8-bit latch will hold an 8-bit value like 25. So use an 8-bit latch. Now what happens? I send 25, 25 comes out from here. So did the latch amplify the signal? No. Did it increase the driving capacity? No. People write these stupid things because they don't know what a latch does. All that it did was input is equal to output. Whatever is the input is also the output. But the important thing is the value also has been stored. It has been latched. Even if you stop sending 25, the bus will now carry 25. Who is sending it? The latch is sending it because the latch has captured the value. Please tell me, did you understand this? Now, how do you use this latch? This bus initially carries address, then carries data. When this bus carries address, ALE is 1. When this bus carries data, ALE is 0. Now, we give this bus to the latch. There are two signals on the latch. OC bar output control, it's an active low enable signal. It has to be always enabled. Active low means it needs a 0, so you connect it to a ground. This is like a formality. Even if you don't show it, doesn't matter. If it's a very strict examiner, might cut marks. So that's why, just to be safe, we've shown it. But that's not where the logic is. The logic is here. There's a signal called gate. Gate means enable. So if gate is 1, whatever comes on this bus will be captured by the latch. The gate of the latch is open. It allows entry. So whatever comes in the bus will be captured. Since I have connected gate with ALE, when ALE is 1, the bus carries address. Address will be captured by the latch. What will come out is also address. Please tell me, did you understand this? Now, when gate becomes 0, the gate of the latch is shut. Input is not allowed to enter inside. Input will come out from here. When ALE is 0, the bus carries data. Data will try to enter the latch, but it is not allowed because the entry is shut. Data will come out from here. From here, you will still get the address. Who is giving it? The latch, because the latch had stored the address. So simple. Once again, this was a bus that carried two things, address and data. First, the bus carried address. That is captured by the latch because ALE is 1. Hence the name address latch enable, because it enables the latching of address. So ALE was 1, so the bus carries address. Now the latch will produce address. Now this bus carries data, but because at this time ALE is 0, data cannot enter the latch, data will come out from here. So this was a bus carrying two things, address and data. What did you do? You fished out address from that and put into the latch. The latch will continue to give the address, the bus is free to carry data. Please tell me, did you understand this? For the last time, I will not repeat this again and again, and for every chips interfacing, this part will be common. So this will be there in every circuit after this. I will not explain it again. So I'm just saying it for the last time. ALE is 1, bus carries address, address captured by the latch, latch produces address. ALE is 0, bus carries data. Because ALE is 0, the gate is shut, data cannot enter. Data comes out from here. What still comes out from here is address, because the latch has held the address. So this bus was initially carrying address and then data. This bus was initially carrying address, later on also will carry address, always will carry address. So this becomes a pure address bus, and this bus is now free to carry data. Please tell me, did you understand this? So this was a bus carrying AD0 to AD7, out of which the latch has captured the address, that is A0 to A7. This bus carries data, that is D7 to D0, which will be connected as the data bus over here. Please tell me, did you understand? What about the higher bus, A15 to A8? Is that a multiplex bus? No. So it doesn't require any latching. It will always carry address. So this becomes your full address bus, A0 to A15, out of which we will be connecting A0 over here to identify whether it's ICW1 and ICW2. We'll be connecting the data bus over here. Please tell me, is this whole upper part of the connection clear? Tell me, did you understand it? If I ask you to draw it again by yourself, will you be able to draw it? Take the multiplex bus, give it to the latch, give ALE signal to the gate of the latch. When ALE is 1, latch will capture address, latch will produce the address now. Bus carries data, ALE is 0. Data will not enter the latch, data will come from down. The latch will produce address. and the bus will carry data. The higher bus A15 to A8 has nothing to do with all this. It always carries address, so it will be given out as a separate higher order address bus. This whole thing becomes the address bus, out of which you will give A0. This becomes your data bus, which will be connected as D7 to D0. Please tell me, are you clear? So we're done with address and data. Now comes control signals. Please pay attention here. 8259 needs read and write. Now 8259 is an IO device. MUPI has read bar, write bar. Students say, why not connect the read bar, write bar of the MUPI directly to 8259? No, my friend, you can't do that. Because this read bar and write bar are active whether MUPI is working on memory or whether MUPI is working on IO. You know memory is different, IO is different. You know the basics of the subject, right? This is a very advanced topic. Your basics, basics were done long back. In the architecture, I've explained what is the role of IO/M bar. Read bar, write bar tell whether it's a read operation or write operation. That along with IO/M bar indicates whether it's an IO operation or memory operation. When you look at all of them together, you understand whether it's IO read, IO write, memory write. Exactly. So we give these three signals, IO/M bar, read bar, write bar, to a decoder, a 3:8 decoder. What does a 3:8 decoder do? It looks. This is exactly what it does. It looks. It looks what's happening over here and gives out output on the other side. If there are 3 inputs, there are 8 different activities that can happen over here. 8 different combinations can appear here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way up to 1, 1, 1. Since there are 8 different combinations, there are 8 different outputs. Whatever is the input, the corresponding output signal will be activated. Are you clear? So once, for 1 minute, just forget IO/M bar, read bar, write bar. Just look at the decoder in an isolation. Just understand a decoder by itself because it's very useful. If the inputs are 0, 0, 0, which output will be selected? Y0. You got that? 0, 0, 1, Y1. 0, 1, 0, Y2, all the way up to 1, 1, 1, Y7. Are you clear? Further, whichever output is selected, that output will be 0 because all outputs of a decoder are active low. That's why we show the bar, that's why we show the bubble. You may show only one of them, that also means the same. You may show both, it doesn't matter. It's just the way of drawing it. So all outputs of the decoder are active low. So for the last time, if the inputs are 0, 0, 0, who is selected? Y0. What does that mean? Y0 will be 0, all others will be 1. Only one output of the decoder can be 0 at a time. The input combination that was given, that corresponding output will be 0, everything else will be 1. Did you understand this? Now that you know what a decoder does, what do we need to do? This decoder is going to observe these 3 signals. Pay attention here. It's going to observe these 3 signals and see what combination is appearing over here, and based on that will announce on that side whether MUPI is doing a memory read, a memory write, an IO read or an IO write. Are you clear? Memory read, memory write, IO read, IO write is what we need to decode from this input. Now, memory read. Come on, memory read. IO/M bar will be 0 because it's a memory operation. Read. So read bar will be 0 because it's an active low signal. Write bar will be 1. We are reading, we are not writing. They are active low signals. The one who is 0 is active. So these two indicate that it's a read operation. This being 0 indicates that it's a memory operation. This whole set indicates that it's a memory read operation. So when processor produces the combination 0, 0, 1, the output that is selected is Y1. That will act as memory read. Why did I put memory read bar? Because whichever output is selected will be 0. So they are all active low outputs. The one who's 0 is the one who's active. Are you clear? Hence the name active low. Now that you understood memory read, answer the rest by yourself. Come on. Memory write. Come on. It's still memory. Memory means 0. Write. So write bar will be 0, read bar will be 1. Please tell me, did you understand this? So this is a write operation, this is a read operation, both of them are memory operations. Are you clear? 0, 1, 0. 0, 1, 0 means Y2. So Y2 will act as your memory write. Similarly, IO read. Come on, a little better now. IO read. IO read is an IO operation, so IO/M bar will be 1. You understand that? It's a read operation, so read bar will be 0, write bar will be 1. Please tell me, are you clear? 101 is Wi-Fi, that will act as IO read. Since 8259 is an IO device, the read that it will get will be IO read. Students say, what is the difference between connecting IO read and connecting read bar? Please answer. If you connect read bar is unreliable. Look at my fingers. Read bar can be 0 for memory read also and for IO read also. But if you connect Wi-Fi, the output number Wi-Fi can only be produced for the combination 101. That means Wi-Fi clearly signifies it is not just the read, it is specifically IO read, and that IO read will be given over here. Please tell me, did you understand? Similarly, IO write. Come on. IO write by yourself. IO. So IO slash M bar will be 1. Write. So write bar will be 0, read bar will be 1. Please tell me, did you understand? This is a read operation, this is a write operation. This is a read operation, this is a write operation. These are memory operations, these are IO operations. So this is memory read, memory write, IO read and IO write. Are you clear? So 110 is Y6. Y6 will act as IO write, which will be given to the write bar of the decoder or write bar of the 8259. Please tell me, are you clear? So this is how you connect your read bar, write bar. Now, suppose I replace this chip with 8255. What's the difference? It is also an IO device. It will also get exactly the same thing. 8237, same thing. 8254, same thing. If I replace this with RAM and ROM are memory. Yeah, so it won't be this. But what? It won't be something else. It will just be memory read, memory write. So if you're connecting IO devices, you'll be giving IO read, IO write. If you're connecting memory devices, you'll be giving memory read, memory write. But the way you produce them will be the same. So this part will be the same. This part will be the same no matter what you're interfacing. Please tell me, did you understand? All of this just looks crazy. When I share these screenshots with some of my friends who are non-engineers and you're just talking, they're like, what do you do the whole day? Okay, I did this. They think, oh my God, what is this? It looking like Google Maps. No, it is not. It is much easier than that. I hope you understood it. Anyway, in a decoder, G1, G2A, G2B bar, these are called enables. Say it again, what? Enables. G1 is an active high enable. G2A bar, G2B bar are active low enables. Do you want the decoder to work? Of course. That means you need to enable it. Since it's an active high enable, it should get logic 1. So you connect it to VCC. These are active low enables. They should get logic 0. So you connected them to ground. You would be saying, why 3 enables? Don't worry. Decoders are not used only over there. Decoders are also used for address decoding. There'll be one more decoder coming in the circuit, and that decoder will produce that final signal that this whole thing is all about. And at that time, we'll be using these signals extensively. In this decoder, we don't need them, so we can't just leave them. You still have to enable the decoder, like you enabled this OC bar by connecting it to ground. You still have to show VCC and ground, but they are not really required over here. They are required in the next decoder that we're going to make for address decoding. Before I start with address decoding, please tell me, is everything shown over here where my hand is moving? Is all this clear? 1 minute recap, please. 8 interrupts coming inside, interrupt going to the MUPI, INTA bar coming from the MUPI, commands coming from the MUPI, A0 to identify the commands, read write to decide the direction of data. To produce A0 and data bus, we need your multiplex bus to be given to the latch. Latch will capture address, the bus will carry data. Out of the address you give A0, out of data you give D0 to D7. For read bar, write bar, you can't just give read write to the MUPI because these read writes are active whether it's a memory or an IO operation. So you need to look at read bar, write bar and IO slash M bar. Not look at one of them, look at all of them together. Looking at all of them together is called decoding. So you need a decoder. The decoder will decode these lines, and based on that we'll understand whether it's a memory read, memory write, IO write. Since these are IO devices, you'll be connecting IO read, IO write. G1, G2A bar, G2B bar are enabled. G1 is active high, so connected to VCC. G2A, G2B are active low, so they're connected to ground. Are you clear? Now, on this side, totally unnecessary. All of this is unnecessary. A lenient examiner wouldn't care about this. Strict examiners, you know how some examiners are. Even things which have nothing to do with the diagram, if you don't show them, they cut marks. So just for their happiness, we are showing them. All of this has nothing to do with the answer that we are discussing. MUPI needs a crystal. Everybody knows MUPI needs a crystal. It needs a clock. Standard operating frequency 3 megahertz. So you connect a crystal of 6 megahertz. Explained in the first lecture. Frequency divided by 2 to produce 50% duty cycle. Anyways, totally irrelevant to the diagram. But some examiners just like a loaded diagram. So you just have to show all this which have nothing to do with the diagram at all. Trap RST 7.5, 6.5, 5.5 are interrupts coming into the MUPI. Hold and HLD are used for DMA. I hope you remember. Hold going into the MUPI, HLD going out. SID, SOD used for serial control. Serial input data, serial output data. None of this has anything to do with the diagram. But like I said, some examiners cut marks. So just to be safe, I've shown it. It's got nothing to do with the diagram as such. So we finished with the interfacing part. Now comes the main signal. Now the level is going to go very high. I want your full concentration. We need to produce a signal called chip select. I've already given you the introduction why we need it. There are so many chips in the circuit. This is not the only chip. When you're working with this chip, only then this chip should be selected. If you're working with some other chip, this chip should not be selected. That means the chip selection is very important. This will come from a decoder on this side of the board. I'll be making the decoder. I've already explained the concept to you. What will happen? MUPI will give out an address. The decoder will decode the address. Depending upon which chip's address it is, it will give out the appropriate output that will be connected to the respective chip, and the chip will get selected. Moral of the story, if we are designing 8259, first of all, to do what we are doing now, you need an address. Most of the times they give you the address in the exam. Design or interface 8259 at the address 80, great, or at the address 40 or whatever. If they don't give an address, you need to assume an address. It's a sum. This is a numerical, what we're doing now. For that, you need a number to work on. So either they will give you an address or clearly write, assuming address of 8259 is 80H, 80. So what is the role of this decoder? The job of this decoder is this one. Okay, that is the block diagram. This is the real circuit. The job of this decoder is to look at the address only when it sees the address 80. That means only when it sees this particular binary pattern. Only then the chip should be selected. The chip select signal should be activated only when MUPI gives the address 80. Are you clear? For that, we need to take a closer look at the address bus. So we start our designing part. Okay, pay attention over here. The first thing you need to make is an IO map. Okay, very simple. IO map A0 to A7, that's your address bus. Because we're doing IO designing, addresses are 8 bits. You can even take A8 to A15. If you know timing diagrams, the address gets duplicated on the lower bus and the higher bus because the address is only 8 bit and the bus is 16 bits. So you can even take A15 to A8. Some teachers do it out of what? Out of kicks. Nobody really does that. Everyone takes A0 to A7. But as a matter of fact, even if you take A15 to A8, it doesn't matter. It's still the same. So I'm taking A0 to A7 standard textbook diagrams. So you take the address 80, whatever is the address, expand it in binary. 80 is 10000000. Are you clear? Now, we need to make a decoder which will select this chip only when the address issued is 80, which means only when A7 is 1, A6 is 0, A5 is 0, A4 is 0, A3 is 0, A2 is 0, A1 is 0, A0? No. A0 can be 0 or 1. A0, pay attention, pay full attention to this point. A0 has gone inside 8259, inside this chip. What is A0 doing inside the chip? Is it gone for picnic? No. The job of A0 is to identify the commands. If A0 is 0, it is ICW1 and others. If A0 is 1, it's ICW2 and others. That means A0 can be 0 or 1. That means this chip will consume two addresses. One address when A0 is 0, other address when A0 is 1, keeping everything else the same. That is how you get the two addresses 80 and 81. Remember the program that we had done? There were two addresses of 8259, 80 and 81. 80 will be the address where you will give ICW1 and OCW2 and 3. 81 will be the address where you will give ICW2, 3, 4 and OCW1. Did you understand? So, for the last time, we are going to select this chip only when the address is 80 or 81. Are we clear? 80 or 81. Any address other than 80 or 81, this chip should not be selected. If it is selected, our sum is wrong. Get this clear. What I'm going to make after this, if 5 marks are there for the decoding, 1 mark is for the math, 4 marks are for what I'm doing right now. You either get these 4 marks or you get a 0. Decoding can never be almost correct. Either it is right or it is wrong. So I want your full concentration here. Okay, once you get it, you know how to do it for any chip. Okay, just 5 minutes, I want total concentration. We again use the decoder. The decoder will put conditions on A7 to A1. Did you understand why I have kept A0 free? Because A0 has gone inside the chip to decide whether it's ICW1 or ICW2. Whether it's ICW1 or ICW2, it belongs to the same chip. So A0 is used for internal selection. This part is used for chip selection. This part has to remain constant. A0 can be any value. That means our decoder will not put any condition on A0. I'll say for the last time, the decoder should select the chip for the address 80 and 81. That means A7 should be 1, A6 should be 0, blah, 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 blah. But no condition on A0. A0 can be 0 or 1. Are you clear? So keeping A0 out of the picture, these are the lines that we need to decode. A1 to A7. For that we use a decoder. A standard decoder to use is 3:8. You can take bigger decoders also. I don't suggest that. The prescribed textbooks use a 3:8 decoder. So I like to stick to that so that you know your answer does not clash with some examiner's thought. Nobody can question a prescribed textbook. That's the textbook the university has told us to use. And those textbooks use 3:8 decoders. So that's why I'm using that. Now, you can give any 3 lines to the decoder. I repeat, any 3 lines. You can give A7, A6, A5, A5, A4, A3, A3, A21, A3, A2, A7 in any order. It doesn't matter. Now what do you want to do? You want to make a random solution or a standard solution? Standard solution, textbook solution, easy on the eye. Examiners knows what the solution is supposed to be. They see the correct solution. Great. You can even make a totally fancy solution which may also be correct. But what are you achieving by that? Nothing, except that you're just telling I am different. And what are you going to do? You're not impressing any examiner, you're just irritating them. Think from the examiner's point of view. They're correcting hundreds of the papers. Yeah, if by doing that you're doing something technically brilliant, yeah, that's fine. It'll end up being the same thing, it's just that it'll just be a complicated circuit. What's the point? So don't harass examiners. Just use a standard solution. Having said that, after you finish this, I'll even show you how to do it by some other combination. But doesn't matter, you're going to end up making the same diagram. So as I said, why harass the examiner? So I'm taking the standard lines. The standard lines are the top 3 lines, A7, A6, A5. This is the standard way of doing designing. What are we saying? We are saying this chip should be selected only when A7, A6, A5 have the combination 1, 0, 0. Are you listening? Now when A7, A6, A5 have 1, 0, 0, tell me, we have done enough practice. 0, 0, 0, Y0 is selected. 0, 0, 1, Y1 is selected. Blah, blah, blah. 1, 0, 0, Y4 is selected. Tell me, did you understand this? So what will happen? Y4 will become 0. When? Only when A7, A6, A5 are 1, 0, 0. No other condition in the world can make Y4 0. Whether you crush the decoder, you smash it, stamp it, boil it, fry it, toss it, do what you want to do with a decoder. A decoder will never give you a 0 on Y4 unless the inputs are 1, 0, 0. Like an AND gate. Do you know an AND gate? An AND gate gives you a 1 when? Only when both are 1. Otherwise, do what you want to do with an AND gate, it cannot give you 1. An OR gate will only give you a 0 when both of them are 0. Otherwise, it can never produce a 0. Similarly, in a decoder, every output can only be produced for one condition. If I see Y7 is 0, if I ever see Y7 is 0, I can bet my life on it and say the inputs are 1, 1, 1. Otherwise, there is no condition in the world that can produce Y7 to be 0. So, if A7, A6, A5 are 1, 0, 0, only then the chip should be selected. Now when A7, A6, A5 are 1, 0, 0, the output produces Y4. Y4 will be 0. That I will connect to the chip select. Tell me, what did the chip select want? 0. Students say, why didn't you ground it? If you ground it, it will always be 0. Instead of grounding, I have connected Y4. What's the difference? Y4 will not always be 0. Y4 will be 0 only and only if A7, A6, A5 are 1, 0, 0. Otherwise, whatever you do, they will not be 0. So what does that mean? Suppose MUPI issues an address 70. Does 70 belong to our chip? No. Our chip's addresses are 80 and 81. 70 is some other chip's address. So should our chip also get selected for the address 70? No. If it does get selected, our whole sum is wrong. Whatever we've done is wrong. If the printer keeps getting selected whenever the monitor is selected, whatever comes on the monitor will go on the printer. Whatever comes on the monitor will go on the speaker. And disaster can happen. You don't want that to happen. So my point is, for the address 70, our chip should not be selected. Now when the MUPI gives the address 70, 70 is 0, 1, 1, 1, 0, blah, blah, blah. A7, A6, A5 will acquire the pattern 0, 1, 1. When they get 0, 1, 1, Y3 will be selected. When Y3 will be selected, Y3 will be 0, which means Y4 will be 1. When Y4 will be 1, the chip will not be selected. That means for the address 70, our chip will not be selected, and that's how it should be. Suppose MUPI issues the address, let's say 40. Now what is 40? 0, 1, 0, 0, blah, blah, blah. A7, A6, A5 have 0, 1, 0. 0, 1, 0 means Y2 is selected. Y2 is selected means Y2 is 0. That means Y4 is 1. If Y4 is 1, our chip will not be selected. Tell me, are you getting a grip on what's going on? So, are we on the right path? Yes. Are we done? No. What we have done so far is called partial decoding. Listen carefully. This is a Viva question. If your Viva is already over, don't bother. Otherwise, it's a Viva question. What is the difference between partial decoding and full decoding? Full decoding is also called absolute decoding, also called exhaustive decoding. Partial decoding is like, okay, yeah, this circuit works. Yes, it works. It will select this chip for 80, will not select this chip for 20, 30, 40, 50, 60, 70. So it works. Is it perfect? No, it's not perfect. This is somewhere in the middle. It's not perfect. Why? What happens? Suppose MUPI gives an address 90. Tell me, 90. Does 90 belong to our chip? No. That means that chip should not be selected. 90 is some other chip's address. But even our chip will be selected because 90 is 1001 blah blah blah, which means A7, A6, A5 are still 100, and if they are 100, Y4 will be selected. That means our chip, that chip will also be selected, but our chip will also get selected. That means our chip will interfere with the operation of that chip. Should that happen? No. Why did this happen? Because we have done half the job, hence the name partial decoding. We were supposed to put condition on A7 to A1. We have put conditions only on A7, A6, A5. Have we? Yes, we have. Y4 is not some faltu line. Y4 is taking three conditions on its head and walking. It is saying I will be 0 only when A7 is 1, A6 is 0, A5 is 0. We have put that condition, but we have not put any condition on A4, A3, A2, A1. That's what we need to do. Are you clear? We are supposed to say yes, A7, A6, A5 are 100, no doubt, but at the same time A4, A3, A2, A1 should also be 0000. So we need to add that extra condition. Are you clear? When we do that, we will cut out all the duplicate addresses. This is called partial decoding. We have done half our job. What's the harm in partial decoding? It gives you duplicate addresses. Not just 80, 81. Any number starting with 8 or any number starting with 9 will select this chip. That means 80 to 8F, 90 to 9F, 16 and 16, 32. There are 32 addresses selecting this chip. There should have been only 2 addresses selecting this chip, 80 and 81. That means you got 30 duplicate addresses. Why are we getting that? Because we have not completed our job. We've only looked at A7, A6, A5. We have to put conditions on the other lines. Let's start. We have to put the condition that A4 must be 0. Tell me what will I achieve by putting that condition? Straight away from 32 addresses, we'll come down to 16. The whole series of 90 will be eliminated the moment I put the condition that A4 should be 0, because in any number starting with 9, A4 is 1. Please tell me, do you understand? So I need to put that condition. Where do I put that condition? G1, G2A, G2B bar. They are not show pieces. I told you they are enables. They are used in designing. G2A bar is an active low enable. That means G2A bar wants a 0. Tell me, do you understand? Now, I don't want to ground it. If I ground it, it's always 0. That means I wasted that pin. I don't want to ground it. I will put A4 over here. Please tell me, did you understand this? If you understood it, tell me the direction. Please, 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 please. I've been teaching non-stop for 12 hours. Please make it worth it. Tell me, what is the direction? From the decoder or into the decoder? Into the decoder. How can decoder produce A4? Who is decoder to produce A4? A4 is a part of address bus. Address is given by the MUP, by the processor. MUP gave A0 to A7, out of which we have taken A7, A6, A5, given it to the select lines of the decoder, telling the decoder only when they are 100 produce the output Y4, which I'll give to the chip select. Great. Now, I've picked out A4 from the address bus and given it as an enable to the decoder. What am I saying? Try to say this in English. This is not a formula or a numerical. This is more like logic. This is telling only when A4 is, yes, only when A4 is 0, this decoder will be enabled and the chip will be selected. If A4 becomes 1, this decoder will get disabled, the line will go into a tri-state, neither logic 0 nor logic 1, high impedance state, no current will flow over here because this device has been disabled. Tell me, did you understand? So that means this chip will be selected only when A4 is 0. That means the whole series of 90 will be eliminated. Tell me, did you understand this? So from 32 addresses, we've come down to 16. Now you got the idea how to make it smaller. We can get it down to blah, 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 till the time we get it down to 2 addresses. Good. So A4 is done. Now I want to put a condition that A3 must be 0. You got the idea. It's not rocket science. Put A3 over here. So A3 will also be 0. Done. Now I got a condition that A2 must be 0. A2 must be 0. G1 is an active high enable, so it wants a 1. It should get a 1 only when A2 is 0. So what do? I put an inverter. Only when MUP gives an address where A2 is 0, this inverter will give you 1, and only then the decoder will be enabled and only then the chip will be selected. Please tell me, did you understand this? Great. So you're done with A2 also. Now leaves only one line. One line is remaining and we are done. But do you understand the decoder is full now? So what do you need to do? You put that extra condition outside using gates. This is where these local author textbooks, I will not even take their names, not really worth it. But the local textbooks, they use a bigger decoder, a 4:16 or a 5:32. What are they trying to do? Deprive the student from using their intelligence. If you use a bigger decoder, you get more enable lines to play with. You don't understand the logic of gates. A 3:8 decoder, perfect fit. That's the reason why textbooks use it, the prescribed textbooks. It's not like they flipped a coin and decided which one to use. This gives you a perfect idea of both. How to do decoding using a decoder and how to manage your gates. That is why most examiners prefer solutions using 3:8. That's why even we use 3:8. Having said that, if your college teacher is lenient use of 4:16, life will be easier. But I'm sticking to textbook answers. So if you use a 3:8 decoder, your inputs are done, but you still have one line remaining, A1, just one line. All I need to do is put a condition that A1 must be 0, only then this chip will be selected. Now till now I was saying Y4 must be 0. This is your good old Y4. Till now I was saying when Y4 is 0, the chip will be selected. Now I am saying Y4 should be 0 as well as A1 should be 0. Who is more important, Y4 or A1? Both. Y4 is the cumulative of the last 20 minutes of logic. If Y4 is 0, that guarantees that all these signals have satisfied your requirement. So you need Y4, but with that you want to put an additional condition that A1 must also be 0. Now, Y4 should be 0 and A1 should be 0. Which gate do I use? Which gate? AND gate? No. OR gate. Say again, which one? OR gate. I will teach you. Why are you worrying? Pay attention. Hey, don't get scared. Very easy. Students say, sir, why not AND gate? Some students, Hall of Fame, they say, sir, why gate? Can you do this? No way. Students say, sir, we do this at home during Diwali lights or during any festivities. We are the ones who connect. We don't call technicians to make those simple basic things at home. We ourselves take two wires, chip off the rubber part and then join the wires with a sellotape and do it. That is possible in an electrical circuit, not in an electronic circuit. There's a big, those wires, those lights that you see are electrical circuits. What's the difference between electrical circuits and electronic? In electrical circuits, all you're interested in is current should flow. I say again, current should flow. In electronics, current has two forms, a logic 1 and a logic 0. Only when you're talking about logic 1 and logic 0, that's when it has become an electronic, a digital electronic circuit. Are you clear? Now, if you just join two lines, what is the problem? I'm going to show you over here. So, suppose I take two lines and this is the output. Students say, what is the problem if I just connect them like this? I'll tell you what the problem is. In an electrical circuit, this is fine because in electrical circuits, I'm only interested in passing current. If this is an electronic circuit, which all of this is, in electronic circuits, current has two forms, logic 1 and logic 0. Tell me, when will this output be 1? When both of them are 1 or when one of them is 1? You got the point. You got the answer already. You keep thinking and by the time answer this. When will the output be 0? When both of them are 0 or one of them is 0? See, that's the point I'm making. There is no logic in this connection. This is just a connection, but there is no logic. Such connections cannot be used in logic circuits. That is why you need gates. That is why gates are called logic gates, hence the name. If you use an OR gate, what's the logic? Only when both are 0, answer will be 0. If you use an AND gate, if any of them is 0, answer will be 0. If you use an XOR gate, if both of them are same, answer is 0, and so on. So each gate brings in logic, hence the name logic gates. You can't just touch two lines and think they are connected. That doesn't work in electronic circuits. So are you convinced that we need a gate? Now let's figure out what logic do we need. When do I need a 0? When any one of them is 0 or both of them are 0? Both of them. Only when both of them are 0, answer should be 0. So the gate to use is OR gate. Now students say, sir, why didn't you use an AND gate? I keep getting calls on this even after the lecture is over in physical classroom. Some students feel shy to ask the question in the classroom. Then the moment lecture is over, they give a call. If you use an AND gate will give you a 0 for 0, 0, no doubt. But will also give you a 0 for 0, 1. Will also give you a 0 for 1, 0. It is a gate which has no characteristic. For zeros, it will produce a 0 for various conditions. It's a good gate to use when you want the output to be 1. But it's a hopeless gate to use when you want the output to be 0 because it will give you 0 for a variety of conditions. Please tell me, did you understand? But if you use an OR gate, yes, you can bet your life on it and say it will give you a 0 only when both of them are 0. That means Y4 is 0. That means all of these conditions are satisfied as well as our new condition A1. Y4 should be 0 as well as A1 should be 0. When all of them are 0, only then the output will be 0 and the chip will be selected and this is done. Tell me, did you understand it? The designing of this chip, then the answer is over. Tell me, is this clear? Now, wait. Hold on. Till here, students understand everything. It's the moment gating is introduced, some people who've not learned gates properly, they get scared. There's nothing to be scared. Don't be scared. There are only 1, 2, 3 conditions you'll ever come across in designing. I teach designing from 8085 to Pentium. There are only 3 conditions that you ever come across. Why? Because when do you need a gate? When you want to combine 2 signals into one. Now, what will the 2 signals be? The output that you need is always 0. The inputs could be either both will be 0 or both will be 1, or one will be 0 and the other will be 1. That's it. Understand the gates used in all the 3 cases and you are a master at designing. Then no matter which processor designing you're doing, you can do it in half your sleep. Look here, which I'm doing right now, not sleep, but yeah, it's 3:15 in the night. If you understood this, it will flow any time of the day or night, doesn't matter. So, I want the output to be 0. First case, I want the output to be 0 only when both inputs are 0. Only when both inputs are 0. Which gate? OR gate. Will only give you a 0 when both inputs are 0. I want the output to be 0 when this input is 0, this input is 1. Don't be in a rush to answer. Your first answer will be wrong. First listen to the question. This should be 0, this should be 1. I repeat, this should be 0, this should be 1. Not even the other way around. Not any 1 0 and any 1 1. I didn't say that. This should be 0, this should be 1. Are you understanding how serious the question is? Only when this line is 0, this line is 1, only then the output should be 0. No gate can do this, because any gate that gives you a 0 for 0 1 will also give you a 0 for 1 0. So this cannot be done by a single gate. You need to break it down into 2 gates. First, make this one 0 using an inverter. Now it comes to your same condition 0 0, use an OR gate. This arrangement will give you a 0 only for the case 0 1, for no other case. Test it. Come on, let's test it. 1 0, 1 1 and 0 0 are the other options. Let's go from here. 1 0. On the top I am sending 1. I don't even need to look down. If 1 is going on the top, the answer will be 1. In an OR gate, if anything is 1, the answer is 1. So this is ruled out, this is ruled out, because again on the top there is 1. I don't need to look down. If there is 1 also 1, the output will always be 1. 0 0. Here I am sending a 0, but this 0 after inverter will become 1. 0 1 will again give you the output as 1. So the only case that can give you a 0 is when the inputs are 0 1. Tell me, did you understand? In memory designing, this is the one used the most. Okay, did you understand this? Lastly, 1 1, I want a 0, simple. NAND gate. How did I get it? Suppose I want a 1. AND gate. I will use an AND gate. AND gate will give a 1 only when both of them are 1. Now how do I make this 1 0? Put an inverter. Now I will get a 0 only when both of them are 1. AND gate with an inverter is a NAND gate. Tell me, did you understand this? As I said, anybody who knows these 3 gates knows designing. Let's go through it once again. 0 0, OR gate. 1 1, NAND gate. 0 1. Inverter and OR gate. The line on which there is a 1, put an inverter and then give both of them on an OR gate. Or the line on which there is a 0, put an inverter on that. Now both have become 1 because you've inverted 0. So 1 1, put it on a NAND gate. But that's a stupid way. That's like catching a nose like this. So nobody does that. And anyone doing it, like, people laugh on it. Anyway, so 0 0 OR gate, 1 1 NAND gate, 0 1. The one that is 1, invert it, now put both of them on an OR gate. Simple ways of handling situations. Please tell me, are you clear? So here our situation demands that both of them should be 0. So you put it on an OR gate. Are you clear? Hold on. Don't be in a rush to close the video. Hold on. Even the classroom when I teach this, students start getting up from the chair. They think it's over. Hold on. Let's do it reverse. Now forget the map, look at the circuit and tell me what is the address of this chip. Somebody gives you the motherboard, you look at the whole circuit, oh, the address of this chip is so and so. You should be able to say that. Okay, if you've done designing, you should know the backward way also. This chip will be selected only when chip select is 0. That means this yellow line should be 0. We are using an OR gate, that means both of them should be 0, which means A1 should be 0. We are putting Y4, that means the input should be 1 0 0. The inputs are A7, A6, A5, that means they should be 1 0 0. Decoder should be enabled, that means G2A, G2B bar should be 0, which means 4 and 3 should be 0. G1 should be 1, since there is an inverter, that means A2 should be 0. If these conditions are satisfied, the chip will be selected. The only line on which we have not put a condition is A0, it can be 0 or 1, which means the addresses are 80 and 81. Now I am not saying it, now the circuit is saying. This circuit is made to select this chip only for addresses 80 and 81. No other address in the world will select this chip. Please tell me, did you understand this? Yes? Good. Now, just to play around with the circuit a little bit, hold on, as I said, don't be in a hurry. A4 should be 0, A3 should be 0. Can I put A3 over here, A4 over here? Of course. There are hundreds of correct solutions and there are hundreds of wrong solutions. Your binary logic has to be right. A3 should be 0, A2 should be 0. Can I put A3 over here, A2 over here? Yes, of course, both of them have to be 0. But the inverter will still be here. Can I remove the inverter? No, because then it means A2 should be 1. Our map says A2 should be 0. So I can arrange it as A4, A3, A2. I can arrange it as A4, A3, A2 or A4, A3, A2 or A2, whatever. There are so many combinations. A1 should be 0, A3 should be 0. I can put A3 over here, A1 over here. Are you understanding? I'm just trying to say, while doing the sum, some people just look around, oh, what's happening? Somebody else's solution might be totally different than yours. As long as the binary logic is right, you will get your marks. You replace this with an AND gate, it's gone. If you if you put an inverter over here, just because you put an inverter over there, oh, I remember there was an inverter, and you put it over here, it's wrong. So the binary logic has to be right. Last point, let's just make it perfect. Let's make it perfect. I'm still giving Y4. I need to put the conditions. A4, A3, A2, A1 should be 0, 0, 0, 0. A4, A3, they both should be 0. OR gate. OR gate will give us 0 only when both are 0. Tell me, do you understand this? A2, A1, they both should be 0. A2, A1, they both should be 0. OR gate. That will go over here. Tell me, do you understand that also? Y4 is clean, everything on the decoder. G1 is remaining. Give IO/M bar. Perfect, done. That means not only should the address be satisfied, it should be an IO operation. Addresses are for IO also and memory also. If MUP gives a memory address, this chip should not be selected. Here, a memory address is 16-bit. Let's say the address is 4080, 4080. In that also the lower byte of the address is 80. That means this chip will be selected. It should not be selected. So for memory operation, the IO/M bar will be 0. The decoder will be disabled. Only for IO operations, the chip will be selected. Please tell me, did you understand this? Now, take any address instead of 80, take 40, 60, 20, take a random number 34, etc. It will still be the same. Let's take 34. Let's take 34. Come on, 1 minute. 34. Suppose I tell you interface 8259 at the address 34H. Why? Because I'm saying it. I'm the examiner. Whatever address I give, you have to do it. 34. A76. It will not take more than 1 minute. 60 seconds on the clock. A7654321 A0. Now, 34 is 0011. 0100. The line which has gone is A0, so A0 can be 0 or 1, so the addresses are 34 and 35. Please tell me, did you understand? Keeping everything else the same. Now this is your decoder, CBA. The lines you will take are 765. 765. So your combination will be 001. Your output will be Y1 going into chip select. A0 has already gone inside the chip, 567 are here. G1 will be connected with IO/M bar, G2A bar, G2B bar. Both want a 0. What is remaining? 4, 3, 2, 1. 3 and 1 are 0. So A3, A1, both of them are 0. OR gate. 4 and 2 are 1. So 4 and A2 are 1. NAND gate. Will give a 0 only when both of them are 1. Please tell me, did you understand? Take any other address. Now you're just playing with zeros and ones. You know your gates, you can handle any situation. I hope you understood this. Wish you all the best. Do well.